Hey guys, my name is Priya and I'm joined by my teammates Jonathan and Matthew, and we're Data Plus Team 13 Agile Waveform Design. So to start off, a little background with our project. Our project was inspired by the Air Force Research Laboratory and their pre-existing projects using their Agile Waveform generators, which are used to generate sensor data. And the waveform generator communication systems are used to respond to attacks by modifying the pattern of transmission in order to avoid jamming. And this is usually outside adversaries that are malicious and trying to steal information or prevent communication. And one way of preventing this jamming is, like I said, varying the pattern of transmission, but this varying of the pattern usually comes with an associated cost, and that's what the base of our project is. And in our project, we created several agents to represent these parts in the communication systems, and we are going to focus this poster on analyzing their strength and testing them against each other. So, hey, Jonathan, are you going through the slides?
Oh yeah. Did you want me to zoom in on one of them? This one maybe?
Everything's fine. Okay. So we were proposed with this game, and it's basically 3 players, a transmitter, a receiver, and an adversary. The transmitter trying to send information to the receiver, and the adversary trying to jam. So the transmitter has n possible bandwidths to transmit information over, and n possible policies. And these policies are basically just the pattern of the bandwidths, and these are predetermined and known to all agents in the game. So the goal is to maximize both Team A and Team B's points. The adversary is trying to guess the bandwidth that the transmitter is using so it can intercept the signal and jam the communication. So to make this a game, we associated costs and rewards with these actions. So if the transmitter is able to successfully communicate to the receiver without a jam, they receive plus R1 points. If the adversary is successfully able to guess the bandwidth and jam the signal, they receive plus R3 points. And if Team A decides to switch the policy, they lose R2 points as a cost.
And so in order to create agents that would be able to play this game successfully and optimally, one thing we looked at is working with several different adversaries and several different transmitters. And this was primarily our focus with these results on the right. But just to briefly go over what kind of agents we had in the game, we used reinforcement learning and recurrent neural network agents. We also used deep Q learning. And what was interesting is we also used a random agent to provide kind of a baseline to see how well the other agents were performing. And we also looked into a mathematical function that could just kind of look at the past and make an estimate of what it thinks the most likely next step is going to be. And so that would be our gamma policy and gamma band is going to look at the past time steps and try to predict what the most likely policy being followed is. And then it's going to choose the next bandwidth based on that policy. We also looked into policy similarity. And so even if you were to randomly generate these sequences or policies, there's going to be, at each time step, there's going to be certain bands that have the same integer. And so there's going to be a little bit of an overlap. But we also wanted to quantify this. And so we developed a metric that could be used to analyze how similar the policies were, ranging from mutually exclusive, where at every time step, the integers are unique, all the way up to the policies being completely identical. And so this metric ranges from 0 to about 1, and it's the average over all time for each bandwidth in the M bandwidths, the count of that bandwidth at a certain time, divided by the total time and the total number of bandwidths. Oops, sorry. Let's see. I don't know if Matthew's here yet. Oh, there he is. Yes, he is. Okay, he can take over.
Sorry, I was just on Zoom problem. So if you could zoom into that top right result, Jonathan. So here are kind of the transmitters and some of the adversaries going against each other. This shows kind of the rewards for the different transmitters, particularly like, as they played with some default parameters, with like game length around 200, 10 reward for successful transmission, 4 cost of switching. And so if you look at this, you could kind of see some interesting trends. First off, the the reinforcement learning based transmitters, which are the DQL transmitter and the RL/RN, which are the green and blue, purple ones, did pretty well against kind of the more random ones, but there's definitely still some weaknesses. For example, if you consider the column with the gamma policy adversary, by far the best one is the self-predicting transmitter, but that actually has the gamma policy adversary inside of it. So it's literally performing mathematically perfectly against it. But it kind of shows kind of the room for improvement these reinforcement learning based agents could have had if they were able to kind of more successfully determine kind of the adversary strategy. And then similarly, and one thing you can note is that against the RNN no policy and with policy adversaries, the transmitter that actually performed the best was the random transmitter, which was actually pretty surprising to us. It makes some sense because a recurrent neural net wouldn't be very good at predicting a random transmitter. So it kind of speaks to the strength of those adversaries. However, these transmitters we did create weren't really able to successfully create a pattern the recurrent neural nets weren't able to predict. One kind of interesting quirk is that the DQL performed extremely poorly against the RNN adversaries. We're not 100% sure why it is. Like the answer we kind of think what's happening is that during training, they're kind of going back and forth, both kind of improving to be the other. But as soon as the reinforcement DQL stops training, the reinforcement, the RNN is able to kind of pick up the pattern that the DQL sticks on as it continues to update. So they're going back and forth, and then the DQ kind of stops changing and is quickly being able to get it figured out. So I think that's why we think that's kind of performing so poorly. And then if you go on to the next slide, like the next graph. So this is the same data, just kind of like more focused on the adversary. So now in the x-axis are the different transmitters. You can kind of see some of the similar trends for example, against the self-predicting transmitter, like a lot of them do particularly similarly, or like really similarly against it. But you can see some interesting results. For example, like against the random transmitter, against the random transmitter, the gamma and the two gamma adversaries, which are the mathematical base, are doing the best. So again, against kind of this randomness, these reinforcement learnings really kind of can't figure out kind of what's the best strategy to follow. So yeah. There's kind of some conclusions and potential next steps. So like against one thing we notice is that against an opponent who plays randomly, the optimal strategy is to use some sort of mathematical formula, and these RL efforts aren't quite able to figure that out. And then while RL efforts show promise against many opponents, more research is needed to improve consistency against certain types of opponents. So future directions we kind of are considering are adjusting certain parameters and hyperparameters, developing a receiver and policy-making agent so that the transmitter could dynamically create the best policy schema so that to like perform perfectly, add rate adaptation and live data signals, as well as improve the DQN's architecture to a double or dueling DQN. Yeah, so welcome any questions.
Thanks a lot. That was really nice. One of the things that it just immediately jumps out at, oh, sorry, there was a question. I thought I saw a hand. No, maybe I just saw a plus. Sorry. One of the things that immediately jumps out at me though is so this DQL thing, it's interesting. So you train it and then the adversary figures it out through the reinforcement learning process. Mm-hmm. It makes me wonder if you kept training the DQL model and then you somehow had some type of maybe split operator where you learn a little bit here, you learn a little bit there, or some type of simultaneous learning, because I imagine simultaneous learning is probably what's most reflective of the real world.
Yeah.
What were you able to ask that? If you weren't able to ask that, was it just time, or was there some inherent difficulty about that?
So it was, I think it was mostly just time. We really kind of were rushing out kind of the last week on it. Yeah. And but we were kind of able to look at kind of live training data like during the process of training. And so it definitely did seem to like the DQL definitely did seem to improve, but it also very much depended on the specific kind of training parameters. If you devoted more computational resources to the RNN, like adversary, it would perform. The DQN like couldn't really figure it out. But if you gave more like opportunities to the DQN, it would do better. I think also part of it was we were doing a very large number of tests and simulations. And so we kind of had to kind of, just because we didn't have like a time to do like 10-hour kind of simulations, we had to be somewhat conservative in terms of the kind of computational resources we gave to the GPU network.
Yeah, no, that makes a ton of
It's
sense.
also interesting because the DQ learning did pre-training and it was updating its resources, like its Q values throughout for each game. So it was retaining that information, whereas the RNN was actually reinitialized for each game. So that's why we weren't quite sure how the RNN was doing better, because it's not like it's memorizing past games like the DQ is trying to do. So I guess just once the DQ is done training, the RNN was still able to figure out the pattern even without past knowledge of the same game.
Yeah. Robert, did you have a question?
I was just wondering. I mean, when the the transmitter was playing randomly, the learning approaches weren't doing all that well. I was wondering if you had, for example, two strategies and you were randomly switching between the two. Do you think the learning algorithms would be confused in the same way?
So I think kind of we have two. The first thing is that's actually something we have originally had in our next step, since we just took off because of just space limitations on the poster. So I think that's a very good question. So my initial inclination is we think it actually might perform okay, just because some prior testing we had done with our recurrent neural networks found that even with switching policies, it was able to pretty quickly determine and pick that up. So we think it would do okay, but we aren't 100% sure about that. At least I personally think it'd do okay.
Okay, that's a great answer. Thank you.
It does seem like this random transmitter gives you kind of a nice benchmark with which you can try to beat, right?
Mm-hmm.
Yeah, and just to go into like a very brief summary of what that does. So instead of trying to evaluate which is the best policy or whether it's better to switch from one pattern to another, all it does is it switches to a random policy with a probability of 1 in 5. And we actually wrote up a little HTML page. There's obviously not room for that on this poster, but you can actually look at the game and see when it switched and when it stayed and how often it was predicted and that sort of thing.
I see.
I guess one thing that your statement just makes me realize is I imagine the amount of time before it switches, so you're uniformly picking between which next channel you're going to, but I imagine the amount of time it switches, there's some distribution you're drawing from, maybe a Poisson distribution or something like this, right?
Right.
And so I wonder if that distribution would impact how well the random receiver does. Do you have any insight? Do you have any thoughts or guesses or insights?
Right. So like we did. Do you remember with the results? We did like explore different parameters. I'm trying to remember if.
Well, I was going to ask real quick a follow-up question to the question, which was you said the random receiver. Did you were you referring to the adversary in that case? As far as how well it's doing?
Sorry. So when the transmitter is transmitting, it's going to stay on a channel until a certain time, and then it's going to uniformly randomly pick a new one. Correct? Or maybe I'm not understanding this.
No.
So this. Go ahead, Matthew.
No, you got it, Jonathan.
Okay. Well, yes, it's switching to a different channel with a probability of 1 in 5. So you end up with a uniform kind of a distribution where like it might stay on channel only 2 times or 10 times or possibly even 20 times.
Oh, so the time is discrete here? It's not continuous?
No.
Yeah.
Oh, so every time step it's switching to a new channel then? With a probability of 1 in 5.
Yeah.
Got it. Okay. Okay, yeah, I think I had in my head that time was continuous, not discrete, but I think that helps. Yeah, thanks.
Yeah, because we were having to generate our own policies and signals, so we didn't have continuous data signals to work with, so we decided it would be easier to work with discrete time.
Yeah, no, that makes sense. And I guess the adaptation to my question would be, if instead of every time step you had some probability of switching, if you had you said we're gonna wait n time steps with p probability, had some distribution on how long you would wait. would that, do you think that that would perform about as well, or do you think that that would start degrading?
I think that there currently is. I'm just kind of. I think it's like a lambda distribution, or it is kind of just kind of at the probabilistic nature. There is like already some kind of decaying distribution of like switch time. I think if you did change it, it would impact results. Also, like if you change switching costs, like rewards, like we chose a ratio of like 2.5 to 1 in terms of like successful reward versus switch costs. But if you kind of change those parameters, like results kind of can be very different. And like
Interesting.
at that point, or like
the results on the right are with what we chose as our default parameters, and that was kind of arbitrarily because of time. We also additionally tested these agents with varying parameters, and we have that data. We just thought seeing how they performed overall with our default parameters would do well. So these are games with length 200 time steps, and then like 10 policies, 10 bandwidths. But there were some changes depending on when we adjusted some of the parameters. We just didn't have the room to include those on here.
Sorry.
I was just going to say, I thought, so Robert had his hand up, and I assumed it was his previous question, but I wasn't sure. Robert,
it was actually my previous question. So Aaron would be.
Okay, great. Aaron, do you want to ask a question?
Yeah, could you guys talk a little bit more about what the gamma policy and the gamma band, it says mathematically based, but sort of how is that actually done?
Yeah, Jonathan can explain that really.
Sure.
Great.
So the simplest one is actually gamma band, and what it does is it looks at the last 5 time steps, and it basically says whichever policy was followed the most recently, the most often, is the one that we're going to be predicting is that the transmitter is on. And the way it does that is it uses an exponentially decaying importance rating. And so the most recent time step might have an importance of say 1.0, then after that 0.3, then 0.09, then 0.0027.
Do you have that Excel spreadsheet open by chance?
I don't, but I can see if I can pull it up. Hold on. This may take me a second.
So that's that's gamma policy, and then what gamma band does is it kind of looks at all the policies it could consider and says which bandwidth is most likely. That way, if they're kind of 2 similar policies, it might choose that that are like have the same bandwidth being considered. It might choose that bandwidth. So it takes the policy information, converts it to bandwidth, and then takes the most likely bandwidth. That's the difference between the gamma bandwidth adversary.
Yeah, so the gamma policy is only considering the past choices and trying to determine which policy was being followed and always choosing that one, whereas Matthew's bandwidth-based one is looking at the next time step and considering it.
Okay, thank you. And so it looked like those did pretty well, if back on your poster, right? For the adversary, those did pretty well for a couple of the transmitter options, right?
Yeah, so especially for the random transmitter, the 2 gamma adversaries seem to do the best. And honestly, the only thing the gamma adversary is predicting is it's predicting that you're going to stay on a certain policy, and it's just trying to figure out which policy that is. And that's one of the reasons why we wanted to look at policy similarity. And so the more similar the policies are, the harder it is for the transmitter to kind of evade detection.
Thank you.
Genevieve?
Oh yeah, so this is a really cool project. So how did you guys kind of take that kind of visual that you had of the game between the transmitter and receiver, the adversary, and like what was the model or like software that you used in order to, I guess, get these calculation of these rewards and then visualize the data here?
But most of it was done with
Python, and then we had PyTorch for the neural nets.
Yeah, so we like built up these we built up the adversaries and the transmitters in Python. So like and then simulate real games playing against each other, calculate reward, and then we have like HTML scripts to kind of upload and look at and analyze these data as well as kind of create these visuals that we're showing. And so one of the great things about that is like we could very quickly kind of create a new transmitter, run it against all the previous ones, or build a whole new visualization based off the data we have. It's a very adjustable and flexible framework that primarily Jonathan built. So big props to him.
Thank you.
Yeah, I was excited when we started putting this all together at the end because there were several ideas. Like Matthew's DQL transmitter was coming in and performing well in certain cases and outperforming other agents, and it was all kind of like each person was coming up with their own agents. And so I think we all started off with the adversaries, and then we kind of moved on to transmitters, and lastly looked at the different policies. But it was kind of fun just to look at to pull everything together at the end and see how they did.
Yeah, Genevieve.
Oh, sorry. Also, follow-up question. So, you guys said that the reinforcement or the RNN was kind of it's like a operant conditioning kind of thing, like based off of how it did, kind of it'll predict based off of previous successes, basically. And then
How the RNN works is it takes in like a sequence. So it's actually looking at previous time steps and taking that as an input. And it's the way I had it set up was actually it's repredicting like its choices for each of those time steps, and then the loss is calculated. It's not considered for like what choice it makes on that time step. It only considers the upcoming time step, but basically the recurrent network is predicting for all those time steps, and it has this hidden dimension that has information that it's carrying through for each time step. So it's considering that whenever the next time step prediction is being made.
okay.
So it's really good at finding patterns.
Does that answer your question? Sorry.
Yeah, my main question was just like, how does that differ from the DQL? Because I'm not familiar with deep learning, so I was just wondering what that like predicts based off of.
Yeah, so I'll try to summarize the kind of key differences. So the way kind of an RNN works is it has like training sample data that it uses to and it considers kind of previous time steps but it's over time it's like it try to optimize itself so that it's the most accurate. So kind of what you're saying about operant kind of over time it'll look at previous data to become the best at kind of predicting the next one. And what deep Q networks do is a little bit different. And what that tries to do is it kind of considers all actions and then tries to predict the reward for the rest of the game for following that action. And over time and over a lot of training, it becomes like it realizes, okay, doing this action means I'm going to get more reward for the rest of the game, whether that's in the immediate time step and in the following time steps. And so over time, it becomes good at predicting like this is the best kind of policy to use in the next time, and that's kind of what happens. So kind of the one is kind of just a predictor of the next policy or the next best policy, and the other is kind of more about predicting reward for the rest of the game. And so in theory, the deep Q network is much better at kind of predicting future rewards, not just kind of current ones. Although one of the reasons it's only somewhat useful in this game is that kind of depending on certain parameters and similarities, you only need to consider kind of future rewards so much. Because like a lot of times steps are somewhat similar.
So would you say that people are more, I guess, have an affinity to use DQL? Like what would you say what we as humans do?
The DeepQL is usually favored for game settings. However, it's a little difficult for our game because it's not a finite game in that somebody wins once you reach a certain point, like the time is finite. This game could theoretically go on infinitely long. And deep Q learning, like for example, I always like to think of chess. It's saving data for every game state, and chess has a finite number of game states, whereas our game, you can have infinite number of bandwidths, infinite number of policies, infinite game length, things like that, and like varying reward that also has to be considered, and not just so like maximizing reward versus just winning the game. So
Yeah.
it's a little bit different, which is why it's not as desirable for our game, but it's still debatable to be more desirable than just the RNN.
So I'm going to kind of give my kind of answer. And I think like the question is kind of is, it depends. I think it kind of depends on kind of the situation. If it's something you're doing kind of for the first time, I would say like you don't have a lot of experience on, you're more kind of using a recurrent neural net, which is like using your past like experience and predict forward. But if it's something you're doing a lot, like even like the way we talked about using a deep Q network for chess, but like I think that's kind of similar to how a human plays chess in terms of it like considers like the next action and then kind of what if I move this piece, what's going to happen, and then all the moves after that. So I think like that comes from playing a lot of chess games and getting experience. So I think like the thing about the deep Q network is it's like relying upon like a lot more of like expectation. It relies upon expectations of future actions. So depending on whether or not you have that, it makes it more or less like a human. But I think that's a really interesting question. So thank you for it.
Thank you.
Also, I just want to, again, we saw some mentions of this in the chat. Thank you so much to Suya for all her help throughout this whole project. She was a real hero and helped us out a great amount. So again, rounds of applause.
Thank you. Thank you to the team also for your great work and for all the efforts you put on this project. I really appreciate.
The session's been great. Thanks for the great presentation and the great work. Let's thank the team. The round of applause.